Welcome. My name is Luann Picard, and I am the chair for the project management department here at UAA College of Engineering. And today I'm your host for the professional development series, and I'm delighted to bring our guest speaker today, Captain James Fry. He is currently an instructor of civil engineering at the Air Force Institute of Technology at Wright-Patterson Air Force Base in Ohio. And we are incredibly lucky. He was just graduated from our Master of Science in Project Management program last December, so it feels like it was just yesterday. He also has a Bachelor of Science in Civil Engineering from Colorado State University and served a total of 7 years as an Air Force civil engineering officer. He's had a wide range of domestic and international experience in Alaska, Korea, around the country and the world, and he is just an incredible student. In his current role, he teaches courses in civil engineering, project management, troop construction, project management, and cost estimating. And his research interests encompass infrastructure challenges, in particular in cold regions, and has an incredible passion for Arctic studies. And his master's thesis last year and his research interest culminated in his thesis, which is about climate change impacts to Arctic airfields. And so we're delighted today to have Captain Fry presenting his work. And I want to also just make a huge shout out today as Veterans Day and just really celebrate this important holiday with our military family, James, his wife, and all of our military members around the country and around the world. So with that, I will turn it over to James.
Awesome. Thank you so much, Luann. I really appreciate the warm welcome. You stole my thunder on the intro, so I don't have to go over that again. So that's great. So I will pop up this slide. So I typically show this to all of my, if I can get it working. There we go. I typically show this slide to all my students as they're coming into class, just so we kind of put a face to a name. So Luann already kind of gave an overview of everything that's up there on the slide. A couple pictures there on the bottom. That's some of my teammates that I've had the pleasure of working with over the years. Some of the Air Force has provided some of the best relationships I've had in my whole life. So certainly grateful and thankful for that. She highlighted my interest in Arctic studies, and I have just a huge interest in anything that's related to the state of Alaska. So that picture over there on the right, folks, if you've never been to it, that's the Army Corps of Engineers Permafrost Research Tunnel in Fox, Alaska. So that's just north of Fairbanks. And if you've never been, I highly encourage you to go. As you walk through, you'll see bison bones and mammoth tusks and things that are sticking out of the walls from 10,000 years ago. Grass that's still green from thousands of years ago. So very interesting. You can go see all the different characteristics in person, see thermokarst and things like that. So just want to kind of bring some attention to that. So without further ado, I'll go ahead and kind of jump into this presentation. We'll kind of leave questions and discussion till the end. But how it's going to roll is I'll give you a little bit of the background of my research project, how it came to be, how we arrived where we're at today, and then the bulk of the presentation will be going over the research itself. And at the very end, I want to tie it together and talk a little bit about the application of project management methodology to this, because I think it's something that's unique to this specific endeavor that I've done. And then, like I said, we'll wrap it up with any questions that you may have. So jumping in a little bit to the project background. So as Luann mentioned, I attended UAA, graduated last year. I believe I reached out to her around 2020 timeframe. I was really wanting to go to UAA to pursue a master's degree. I wanted to do it in project management. The Air Force was requiring me to complete a thesis option, which was not something that was offered through UAA in that program. So ended up working with her in the department. And they opened up a pilot program for me to go ahead and complete a thesis in an engineering topic while still accomplishing all of my project management curricula. So that's essentially where we're arriving at with the start of this project. So kind of opened up the door for that opportunity. So I'll kind of go over how I arrived on the particular research topic that I did. So just given my background as an Air Force engineer, I have a large interest in infrastructure as well as Arctic studies. So really kind of started narrowing down my scope into something to do with permafrost, something to do with climate change, and something to do with infrastructure in Arctic regions. So there's this thing called climate change that I think a lot of us are acutely aware of. It's something that's been acknowledged since the 1980s. And the consensus today really is that air temperatures are warming around the globe, and particularly in Arctic regions, they're warming about twice as fast as global averages, largely due to Arctic amplification, loss of sea ice, changes in albedo. So it's certainly amplified in the polar regions. So what exactly does this mean for Alaska? Looking through my particular lens, looking at infrastructure, we kind of started to look at it from that perspective. So just throwing out some definitions. Permafrost, if you don't know, is just soil that essentially remains at or below 32 degrees Fahrenheit for 2 or more years. So it's essentially just that. It's frozen ground. And if you look throughout the Northern Hemisphere, it occupies about 24% of the landmass in this hemisphere, obviously a large portion of which is the state of Alaska. So started looking at permafrost prevalence throughout the state. If you look at the map on the left-hand side, you'll see different zones of permafrost. Largely north of the Brooks Range, you'll see most of those soils are continuous permafrost. The interior of Alaska is largely discontinuous, so it's in pockets, and then moving into sporadic and really not a lot of permafrost around the Anchorage area. That's just kind of showing throughout the state how it changes. If you pan over to the map on the right, this is essentially overlaying a lot of our major roads, a lot of our major communities, a lot of our major airfields throughout the state, and overlaying that over that permafrost map. And you'll find that about 40% of Alaska's airports are susceptible to changes in permafrost. And what I mean by that are phenomena such as localized subsidence or long-term consolidation as permafrost degrades. So this essentially kicked off my thesis in general, and from this information, I was able to develop a main research question, which is up here on the screen. So to what extent have changing climate and permafrost conditions impacted constructed airfields in Arctic and subarctic regions? So specifically looking at those climate change impacts to Arctic airfields, as my title would suggest. So how did I go about doing this? This is essentially my research scope baseline. So partnered with the Alaska Department of Transportation, worked with one of their pavement engineers, Mr. Drew Pavey, and he was very, very helpful and insightful into narrowing down some locations to really focus the study around. And you'll see the locations up here on the screen. We have airfields at the locations of Barrow, Nome, Kotzebue, and Clear, and those are indicated on the map as well. Had numerous selection criteria for picking those locations. I really wanted airfields, that we're comparing the same type of material from location to location. So all of these airfields have asphalt pavements, so we're comparing apples to apples as far as pavement health. I wanted locations with representative permafrost conditions. So if you refer back to that map that I showed you previously of continuous, discontinuous, and sporadic zones, each of those locations would be representative of those different zones of permafrost. Also looking at the quality of pavement evaluation history. So the Alaska DOT is very, very good at upholding every 3-year rotational schedule as far as their pavement evaluations are concerned. So all of these locations had pretty much an inspection done every 3 years for the past several decades. So it was a very comprehensive, very good data set. Also was looking at geotechnical data. So anytime there's a construction project or some sort of geotechnical exploration, boreholes, was able to compile and consolidate all of that data that the DOT had provided for all these locations. And it also similarly went back several decades and was kind of in alignment with the pavement evaluation. So that provided good means of comparison as well. And then with all these locations being airports, there's likely a weather station or some sort of weather monitoring device that was able to capture weather data or climate data through time. So that was a pretty easy grab as well. And then the last selection criteria that I had up here for this particular research, just bringing some value back to the organization that I work for, was having some sort of Department of Defense interest at all of these locations. So whether it be different radar sites or other mission sets that supported the Department of Defense, that was also included in the selection criteria. So jumping into the climate analysis and how that was conducted. So there's a wide variety of climate parameters that you can look at when you're approaching a problem set like this. The one that I really focused on was temperature. So past research has confirmed that there's a link between permafrost degradation and variations in air temperature. And the consensus largely is that as air temperatures increase, that's going to drive warmer permafrost, and it'll eventually degrade. So you'll see one of my first research questions up here: how can each location's climate be characterized for data analysis? Primarily did this through freeze and thaw index. And this is just an example of how some of those computations work. So you grab a mean daily average temperature at one of these locations for a particular day, and you would calculate the difference between that temperature and the freeze point. So number of degrees below freeze point would indicate a freeze index. A number of degrees above freeze point or above 32 degrees Fahrenheit, that would indicate thaw index. You sum those values over a calendar year, and we were able to compare that over long time scales. And the result of that is found on this slide. So you'll see for all 4 of these locations, I have freeze and thaw index graphed for a couple decades, and you'll see that there's a decreasing trend in freeze index. Those are going to be the blue dots on these graphs at all of these locations, as well as increases in thaw index. So at Nome and Clear, you may notice that the thaw index is actually exceeding the freeze index in some years. So that's really very indicative of a warming climate, and certainly does illustrate the temperature phenomena that is occurring at all of these study locations. So it's kind of wrapping up like the first part of our climate assessment for these sites, and moving on, kind of want to dive into physical characterization. So some additional definitions I want to toss out there to you, specifically related to permafrost, would be ice-rich, thaw, unstable permafrost. So we were talking about frozen soil that contains a high enough ice content that it's going to become unstable when thawed. So when you think of, I really want you to think of smaller diameter soils, think of silts, think of clays. These soils are going to retain a lot more moisture, and obviously when that moisture freezes, it's going to expand and create a larger volume. And then similarly, when that soil column thaws, that moisture will melt and drain, and that volume is going to change a great deal. Conversely, looking at ice poor thaw stable permafrost, that's frozen soil that has tiny amounts of ice, and they're going to show a minor change in soil volume when thawed. So think of well-drained soils such as sand, such as gravels, things of that nature that aren't really going to have a major volume impact when they thaw out. So this slide, it has a lot of information on it. I'm going to do my best to kind of break it down for you. So these are all nominal geotechnical profiles that I constructed from borehole data to represent each airfield. So you'll notice that at Barrow, Kotzebue, and Nome, those are the 3 there on the left, they all show presence of permafrost soils in the column, and they all have upper extent degrading over time. So that's shown by the black bars on the left-hand side of each of these soil profiles. There are variations in data that were encountered, and that's largely due to the spread of borehole locations with time. So the DOT wasn't necessarily going in and conducting boreholes in the same exact location every single time they were doing an exploration. So for example, permafrost data at Nome, it was actually consolidated from an area of boreholes that are about 150 feet wide by 2,000 feet long. And if you're familiar with any types of geotechnical investigations, you know that there's going to be some variation there. That's largely what's leading to some of that variation in upper extent measurements. If you pan over to Clear, you'll notice that that location that's located in interior Alaska didn't really show evidence of permafrost soils at all. So I do want to take a second here just to emphasize the importance of why we were looking so closely at these soil profiles. So as previously mentioned, all of these airfields, they're surfaced with asphalt. And asphalt is much unlike concrete in the fact that it's not a structural member. It's not designed to carry the load of the aircraft or the vehicle or anything that's traveling on top of it. Rather, it's really designed just to transfer and distribute loads to subsurface layers. So that's really why it's so important to have proper embankment design and proper embankment construction, because that's going to be all the more critical than the paved surface itself as far as performance over a long time span. You'll go in, you can mill an overlay, or you can do a full depth repair on a surface, but your embankment's largely going to be there a lot longer than the paved surface will be. Metaphor that I really like to use is, if you lay out carpet on a hardwood floor is still bearing your load, whereas the carpet's just making that a nice wearable surface to travel along. So you'll also notice that at all of these locations, the upper layers, they have diagonal hatching through them. And that's just indicating that those are fill material. So that material is specifically brought in during the construction process and compacted to the embankment. And that's primarily what's going to be used to support traffic loading. Typically, you're going to want gravels. That's kind of what you're looking for. They're well drained. They're not going to hold water, kind of going back to that thaw stable permafrost definition. And it's typically what you're wanting for these construction projects. So you'll see gravels in orange on these soil profiles. Also note that 3 of these locations are in coastal regions that are not on the Alaska road system. So naturally occurring material at these sites is typically not that nice, well-graded gravel that you'd want to construct with. So you can see that reflected at locations such as Nome and Barrow. Barrow, for instance, is the most northern location. It's the farthest from any road. You have to barge any of your material in. Gravel is simply not a feasible option for the DOT to put in there, and sand is really the best we could get sourced locally. So as you get deeper in these soil profiles, you'll notice that there is a transition to smaller and smaller diameter soils and a greater amount of organics. So this is material that you're pretty much trying to avoid, especially in a permafrost type environment. Looking at Clear, though, our interior site, it's located on the Nenana River. That's a lot of gravel there, so you'd probably expect a better performance out of that airfield than some of these others. So the key takeaway from this slide, just looking at the sandy, silty, and organic subgrade layers at Barrow, Kotzebue, and Nome, they all had varying levels of ice content and had varying levels of frozen soil classification from VX to NB, which, if you're familiar with those, it basically means that it's thaw unstable, and you can expect high consolidation rates as that permafrost degrades. So moving on, a closer look at the measured data from these borehole logs at each of our study location. We got these graphs. So upper extent of permafrost for each borehole, I graphed that against years explorations were conducted, and you can see there's a clear trend at all 3 locations that the upper extent is deepening in the soil layers. So that's indicative of degradation. Upper extent was pretty much the best parameter that we could pick. Most of these boreholes were drilled to about 20 to 30 feet in depth, and that really wasn't getting down below the actual permafrost layer. So there's still permafrost present at that. So upper extent was the best we could get as far as parameters. Nome was the exception. Most of those boreholes were getting below the permafrost table, so we could get an upper extent, a lower extent, and actually calculate a thickness off of that as well. And in fact, the most recent geotechnical investigations from 2019 at Nome showed that permafrost had degraded entirely at most of the borehole locations on that airfield, with little to no frozen soil currently present. So I want to compare that data with some other concurrent data that's been going on across the Northern Hemisphere. So if you're familiar with the Circumpolar Active Layer Monitoring Program, or the CALM program, they have a variety of stations located throughout the Northern United States and Canada. And several of them have a very close proximity to the selected airfields for this study. So the primary goal of CALM is to observe the response of active layer in near surface permafrost to climate change over long time spans. So active layer here is defined as that portion of soil that sits above permafrost that thaws and freezes seasonally. So comparing that with upper extent data and thickness data, you can see here at Nome that Nome's permafrost thickness are decreasing and converging to 0 by 2019. And then looking at the CALM data sites, you'll see that active layer is increasing as well. So both very indicative of degradation. So just kind of validation of both data sets. So a main research goal here, obviously, was looking at pavement health. And I was wanting to pair these climate trends with pavement inspection data and really assess if there was any correlations there. So procedures for conducting pavement evaluations largely uses a visual distress rating system that's called PCI, or Pavement Condition Index. And this is a numerical indicator, and it just rates surface condition. So if you have a pavement with a score of 0 or a PCI of 0, that's denoting that that pavement is completely failed. You're not going to be able to use it. Whereas a PCI score of 100, that means that that's a brand new pavement. You just had it come out the paver and you just compacted it and you're good to go. So regularly monitored PCI ratings did exist through those evaluations the DOT had conducted. And this helps entities and airfield owners really identify early on the need for major repairs, and you can kind of use that as a forecasting tool for when you're going to need to have some sort of construction project to go in there and fix that. So selected this as a key metric for this research just because it was standardized, it was available, and it's pretty standardized across the nation. In fact, back in the 1970s, the Army Corps of Engineers developed a pavement management system called PAVER, and that's adopted by most government agencies throughout the United States. The Alaska DOT uses this for their tool as a primary tool for conducting pavement evaluations and pavement management for their airfields. And I was given access to that pavement management system, which was very beneficial. So jumping into a little bit of the pavement analysis. So there's a very helpful function in this software called family modeling. And this tool pretty much enables you to generate a pavement degradation curve. And that's based off of inspections that are conducted throughout the whole inspected lifetime of an airfield. And it's going to graph a calculated PCI for every inspected section against the age of the pavement sample. And then PAVER will match a closest fitting polynomial curve to that data, and that's what you're seeing up here on the screen. So like I said, this really helps infrastructure owners forecast when you're going to need some sort of major rehabilitation. So for example, this curve that I have up here on the screen, this is from a combination of 10 asphalt airfields that are in the lower 48. I actually pulled this from data from the Air Force Civil Engineer Center. So these are all from Air Force bases that have asphalt runways. In the lower 48, up in the top or upper left, you'll see you started a score of 100, and then over the period of about 40 years, you're degrading to a PCI of around 55. So that's essentially what this curve is representing. So we're going to compare this with several other airfields, including those in this study. So this green curve that I have up here on the graph, this is representing an airfield in South Central Alaska. And just being transparent with this forum, this is Joint Base Elmendorf-Richardson. Just kind of comparing. These two orange curves are representing airfields in Inferior Alaska. So Clear Airfield is the one with the dots, and then the other orange curve, that's actually Eielson Air Force Base up in Fairbanks. Adding some more curves onto this plot, you'll notice that these are Arctic airfields in zones of continuous permafrost. So Barrow, Kotzebue, and Nome, which are all airfields within this study. And what I really want to bring your attention to is this black line now. So this is denoting a PCI score of 70. So the Alaska State Legislature requests that the DOT maintains their runways to a surface condition of 70. That's primarily for aircraft safety, just so we can ensure safe landings and takeoffs, and passengers and cargo are getting where they need to go. So notice that Arctic locations with permafrost are typically degrading to that PCI score of 70 within 4 to 8 years, while other locations on this plot are taking 12 to 18 years to degrade past minimum standards. So that's a large variance there. I do want to bring up that there's going to be a host of factors that impact that rate of degradation. That includes traffic, what kind of aircraft are landing, their tire pressures, their wheel patterns, what sorts of maintenance strategies that are used at these airfields, how often those maintenance strategies are employed, quality of your construction, how much funding you're getting, environmental, climatic variations, right? There's a lot of things that play into this. But specifically for this study, we're looking at how this data connects to permafrost degradation. So I'm going to dive a little bit more into how we conducted that analysis in comparison. So showing you these different graphs, these were generated out of another tool in Paver called condition performance analysis. And these are essentially tabulated data sets for every airfield that I generated to show PCI deduct values per year since initial construction. So that's essentially establishing a degradation rate for each inspected section. And I plotted those degradation rates against permafrost upper extent at those locations for the same time period. So previously we talked that the upper extent of permafrost will deepen into the soil profile as degradation continues. You'll notice that there's a general increase in PCI degradation rate with deepening upper extent of the frozen soil for Barrow and Nome, and there's a slight increase here for Kotzebue. So to make this a little bit more readable, I'll show you this plot. So if you consolidate all of that data onto a single graph, this is what you get. And you'll see that average PCI degradation rate for each data set, those are going to be shown with those triangular points. And then upper and lower bounds are shown by the bars at each end of those whisker plots. So like I said, it's important to note that there's going to be other factors that affect degradation rate, pavement, age of pavement being one of them. But this regression model did produce an R-squared value of 0.4872 when we're comparing that degradation rate to upper extent of permafrost. Further investigation showed that a lot of these extremely high values up here on the top end of the plots, those were associated with pavement sections that historically had recurring problems with differential settlement that were confirmed to be attributed to permafrost degradation. So that's likely what's driving up a lot of these averages over here on the right-hand side. Now, PCI isn't going to tell the whole story here. So PCI is derived from distress data, and distresses are just external indicators of pavement deterioration. So when an inspector goes out, they're looking at different types of distresses and aggregating those into Paver, and that's what's going to calculate your PCI. So these pavement deteriorations or distresses are caused by loading, they're caused by environmental factors, and they're caused by construction deficiencies, and it may be a combination of any of the three. So what I did here was I developed parametric unit costs based off of the best practice for repairing each of these distresses, and was able to determine a lifetime treatment cost based off of how many distresses were located in each airfield. So basically breaking down this graph, let's take a look here at Kotzebue, for example. You'll see this large section here in the middle that's orange with 50%. So what it's saying there is at Kotzebue Airfield, 50% of the lifetime treatment cost to repair that airfield was coming from the distress of block cracking. So that's all this data is saying. And we're going to clear this up here in a little bit, make it a little bit more readable and pertinent to this study here in a second. So what we ended up doing, we're classifying distresses broadly into three different categories. You will see every distress that is available in the Paver database that you can assign deduct values to, located over here on the right. And from past research, we're able to associate several of these distresses as being permafrost associated or cold regions related. So depressions and longitudinal and transverse cracking, we classified as permafrost associated. Block cracking and raveling, which I'll show you some examples here in a second, we considered to be cold regions related, and then everything else just lumped into the other category. For this research, we're not saying that every single recorded distress is in fact caused by permafrost degradation or extreme cold, but we're assuming it for this study just based on past research. So here's some examples of some of those distresses. So you'll see up here on the left, here's a depression on runway 1028 at the Nome Airport. So when you go out and inspect an airfield, oftentimes it's hard to pick these out, especially if it hasn't rained recently. But if you have had a rain event, it's pretty easy to identify just anytime there's some ponding or something like that. So you'll see that's an example of a depression caused by subsidence at Nome. And then over here on the right, you'll see some longitudinal cracking that's on a rolled shoulder that is from permafrost. It oftentimes does occur on the shoulders, but it oftentimes can extend into the actual pavement section itself. And in fact, in talking with a bunch of the engineers at the Alaska DOT, these longitudinal cracks are not just going through the pavement surface, they're going deep into the embankment as well. So these are ones that we're considering are permafrost associated. Some of the cold region related distresses that we identified were block cracking. So you can see that there on the left. And block cracking is largely attributable to extreme temperature cycling. So in a lot of these locations, you're going from, -60, -50 in the wintertime to, up to 90 degrees in the summertime sometimes. So that'd be an example of what, temperature cycles would result in. On the right, you'll see raveling, and raveling, especially in these locations, is largely going to be attributed to just damage from snowplows scraping the surface of these airfields time and time again, and you kind of see some different severities there. So with these defined, we applied that to that previous cost model that I showed you and developed this plot. So after applying that to this model, you'll notice that the majority of distresses were climate driven at Barrow, Kotzebue, and Nome. So on the other hand, when you're looking at clear, just over a quarter of the distresses were cold region related. So note, want to recall that the quality of embankment material and the lack of permafrost at clear were probably attributing to this. But from this analysis, it's evident that the presence of permafrost and extreme cold climate are impacting what types of distresses we saw, and they are driving costlier maintenance and repair. So for this particular model, 91% at Barrow, 81% at Kotzebue, 49% at Nome are representing the percentages of lifetime treatment costs that were permafrost associated or cold region related. And these locations also correspond to the highest PCI degradation rates that we previously investigated. So at clear, only about 28% of the distresses were considered in those categories. That was the first cost model in this study. I'm going to walk you through another one. So while I use parametric costs and from published cost manuals for that last one, primarily RS means is what I used to develop those cost estimates. This final analysis was really using historical data from the Federal Aviation Administration. So the FAA has something called the Airfield Improvement Program, and it provides federal grants for major rehabilitation and reconstruction projects at public airports. So the state of Alaska largely leverages this and takes a lot of federal help to get a lot of these major rehab projects done and funded. So all these project costs and all this data, they were reflected to and adjusted to reflect 2021 US dollars. So just factoring in inflation there. And this is only a single data point in the terms of like actual recorded costs. So this does not include preventative maintenance. This doesn't include state-funded projects, but as I said, the state largely leverages this for a lot of their major projects. So this is a valuable data point to consider. So the graphs that we have up here is for each location, showing the major airfield improvement program funded projects at those locations, their amount in dollars, and the year that they were awarded. I also included area weighted PCI in green, just for latitude. So you'll notice on all of these plots, whenever there's a major project that occurs in the red, you'll see there's a latent response in PCI in that green curve. So, and that's basically validating the data set, saying that, hey, as we're spending money, our PCI help is increasing a few years down the road. When we get an inspector in there saying like, yep, those repairs were actually valuable, and it's bumping up our PCI and our pavement health, and we're able to prove that quantitatively. So taking all this data, we're going to compile this once again on a single plot. And this is consolidating yearly grants for all airports at all of our study locations, and developed a cumulative cost curve in orange for the past 37-year period. You'll notice that this data shows that rehabilitation and reconstruction projects funded by AIP exhibit several increasing rates of change during a couple different periods at these study locations. Those relative spikes in funding. They are indicated by the black arrows, so we'll remember that here in a second as we move on. But specifically, why did these rates increase over these time periods? It's going to take a bit more of a thorough investigation of the AIP grant program, and I'll just take a moment, a minute or two, just to explain some further analysis, just trying to explain why those funding spikes may have occurred. So using employment data, I chose 3 additional airports in the lower 48, just to kind of compare to our Arctic airfields. Filtered all of the airports in the U.S. by service level and type of hub and material and all of that, and selected an additional 3 airports at Yakima, Washington, Fort Smith, Arkansas, and Cody, Wyoming, just for comparison. And these airports are located across a multitude of climates, and they're assumed to be representative of the greater AIP sponsor population for this size and scale of airfield. So you'll see these are all cumulative cost curves for the AIP program. The total amounts of grants dispersed show that study airfields are in fact receiving more funding than similar airports in the contiguous U.S. So increased costs could largely be attributed to greater maintenance and rehabilitation. Might be caused by dynamic permafrost conditions. It might be other economic factors. We talk about the remoteness of our study locations, the increased travel requirements, the shorter construction seasons, limited availability of qualified contractors to go up and do the work. We have a lot of challenges related to executing these projects in Alaska. So those can, obviously are playing in here. I do want to point out that the cumulative costs over here are correlated to latitude. So you'll notice that our more southerly sites are costing more. So that as you actually get further north, it's costing more. And there's some postulation there that perhaps our discontinuous locations are at higher risk of permafrost degradation and impacts to infrastructure than our more northerly sites that haven't seen as much degradation. Just wanted to throw that fact out there. So another thing I want to bring up is, locality differences do exist. Obviously, things in Alaska are costing us a lot more. My work in the DoD, it's very prevalent as we do cost estimates and manage projects. So we largely employ things such as area cost factors. So I was just looking at some DoD publications, and if you look at Anchorage, Alaska, compared to the U.S. baseline, the area cost factor in 2021 was 1.9. So we're saying on average it costs 1.9 times more to do a project in Anchorage than it does for the U.S. baseline. So once again, kind of some contributions towards some of the data that you see up here on this slide. So rolling back to the previous cost model that we were looking at, those relative spikes, I also plotted up on here thaw index, the average thaw index for all of our study locations, and those are graphed in red points, and those are clearly on a positive and warming trend. I want to point out when years that the thaw index deviates significantly from the mean, we're identifying those as local maximums. Those are yellow points on the graph. So these maximums, they're representing the highest number of thawing degree days in a calendar year that have been experienced in recent history. So years with greater thawing degree days can accelerate permafrost degradation. You're deepening in that soil profile. You're thawing more things out. And you'll notice that when we have those relative maximums and years when the thaw index reaches a new high, those are consistently followed by spikes in grant funding. So just note there's a correlation there. There still needs to be further root cause analysis and a lot more investigation to assign true causes to what would be causing these funding spikes. But this correlation here, it can prove useful to airfield owners when we're monitoring climate conditions and potentially forecasting future budgetary requirements and future programming requirements for some of these airfields. So just bring it home with the research here, I just want to summarize some of the research conclusions. So we're able to find that calculated air indices at all these study locations, they do indicate warming trends over the past 20 to 30 years. The freeze index was shown to be decreasing with time at all of our study sites. The thaw index was shown to be clearly increasing at Kotzebue, Nome, and Clear. Concurrently, permafrost's upper extent decreased with time at Barrow, Kotzebue, and Nome. Permafrost at the Nome airport had degraded most entirely at all borehole locations by 2019. And this was shown through the aggregation of borehole log data that showed the extent of frozen soil. We used family curve tools out of Paver, and that enabled the generation of some degradation curves to show side-by-side comparison of airfields. And that showed that study airfield pavements were shown to degrade 2 to 3 times faster in continuous permafrost zones compared to discontinuous regions and locations in the lower 48. Curves from Barrow and Nome, those degraded to a critical PCI 3 to 4 years post-construction, respectively. Nome reached critical PCI after 9 years. Clear reached it after 20. So for reference, the consolidated data from 10 airfields in the lower 48, as a U.S. baseline average, it took about 16 years to degrade to critical PCI, just for comparison's sake. Study airfields constructed on permafrost, they did exhibit a preponderance of permafrost-associated and cold region-related distresses. So measurement of the most costly distresses gauged economic impact at these study airfields. And the definitive cause of these reported distresses is not confirmed, but it's suggested based on research of permafrost degradation in extremely cold climates. And then finally, looking at our cost models, the cumulative cost to rehabilitate or reconstruct study airfields from the Federal Aviation Administration Airfield Improvement Program and that grant program, it has increased since 1983. The grant values were continually increasing with time, even after adjusting for inflation. And then when comparing that to climate data and historical maximums in thaw index at all study locations, those were followed by spikes in grant funding. And as I stated before, those potentially could be used as a forecasting model for infrastructure owners in this region. So that's, in a nutshell, a quick summary of all the research. If you're really interested in it or you want to go read it, feel free to go take a look at my thesis that's out there. I do want to bring this presentation home with just a little bit of the application of project management that I used to conduct this research. So I think most graduate students probably aren't thinking through this lens. I think most of them are just working with their advisors and they're going out and they're trying to get their work done as soon as possible. But working with the MSPM department, Luann in particular, on how to successfully get as much value out of this as possible. I actually created and employed a project management plan for this whole research project. I made a schedule. I tracked progress. I established key performance indicators. I was monitoring and controlling this project from the very beginning. I had a communications management plan. I was looking at stakeholders. I had, was establishing expectations there. I was managing change, managing risk, doing all of those different knowledge areas throughout this whole process. And I think it worked out very, very well. Ended up delivering my thesis, but on time, if not ahead of schedule, and graduated on time. And considering the time frame I had, about 16 and a half months, I could certainly consider that a success, and I'm very happy with the results of everything. One of my colleagues that's inbound to our schoolhouse here, he called me the other day and he's like, hey, I'm going to have, I'm still coming in January, but I'm going to have to finish my thesis next quarter because we just couldn't get it done in 16 and a half months. So seen a lot of folks having issues with that. So I think that's a result of using proper project management and getting a lot of value out of that as well. So with that, that's been about 40 minutes of me talking. I will open it up to any questions, comments, or any discussion that anybody in the room or anybody online would like to bring.
Well, thank you so much, James. Again, it's just really such a nice serendipity that we have Veterans Day and we have an active military student graduate presenter. It's just a really nice convergence of all of those things. So thank you so much for your wonderful presentation. Andy, I'm going to ask for your help for anyone in the room who may have questions and anyone that is on remote that has questions. Can you help me with that, please?
Sure. So yeah, we don't have any questions online. Anyone in the room have a question? Go ahead.
I have one question. When you were looking at the pavement degradation, now you mentioned drainage at one place, but how much did you take drainage in consideration? Was that a major problem in some of these areas? Permafrost or subgrade not draining properly?
Certainly, yeah, it's a really good question. I would say more subjectively than quantitatively. So, if you pull up satellite imagery of Nome and Kotzebue, for instance, a lot of that's built up out of very coastal regions. There's a lot of ponds, a lot of lakes, things of that effect that are close by. That can certainly affect pavement degradation as well. As you add, water on top of a soil profile, that's going to change your thermal regulation and everything. So that's certainly in effect. But for this particular research, had to keep somewhat of a defined scope, so we didn't really look at it numbers wise. Hopefully that answers your question.
Yeah, that answers it.
What is the jet blast erosion?
Are you talking specifically for distress?
Yeah, the asphalt.
Right. So when jets are taken off, that's a lot of thrust coming out of jet engines, and that can actually cause a damage to your asphalt wearing surface. So you can actually be burning off oils and emulsives and things like that, and exposing aggregate. So that's a commonly seen distress, especially at the ends of runways, as you're getting that first push for takeoff, getting a lot of thrust out of your jets. So you'll see that commonly at the ends of runways.
All right.
Did you go to visit each of these sites personally? Have you been to all these sites as well? Just out of curiosity.
Unfortunately, I didn't get the chance to. I've been to Clear just because it's off the road system, so I was able to drive up there on another trip and see it. But just due to travel constraints and everything, I wasn't able to actually travel out to these sites. I really hope to at some point. It'll be really neat to actually set foot on them one day. But yeah, everything was just from my computer, unfortunately.
Thank you.
Great.
All right, in this lull between, I just wanted to mention that the password for today's survey is impact, all lowercase. And Luann, go ahead.
Yeah, I was just going to say thank you for everyone who joined today. It really was a privilege to bring one of our student graduate leaders and amazing industry professionals and veteran active duty military personnel talking to us today about this important topic. I think there's a lot of, besides just the research itself, I think there are a lot of really interesting lessons about how these kinds of impacts can affect cost estimates and infrastructure viability in the state of Alaska. And I know he talked about this, but I think there was a lot of very great partnership that went on in this project, not just with the DoD, but also with the Department of Transportation. I think a lot of interesting data was provided that was very compelling for them as well, and made a difference in their own ability to estimate infrastructure maintenance costs beyond runways themselves. So I think James's work is beyond the specific topic and can actually be very helpful to others. So I want to thank you, James, for being here today. Thank you to everybody for joining us locally and remotely. And with that, Andy, I'll turn it over to James, I'll turn it over to you to wrap up, and then Andy to close us out.
All
Perfect.
right.
Thank you. Yeah, thank you, Luann. I just want to say thanks to everybody for braving the storm. I'm down here in Ohio and 60 degrees and no snow. So thanks for coming out and bearing 2 feet of snow. I miss it dearly up there. So enjoy it.
Thanks.
All right. Thank you very much. Okay, be sure to join us for our next professional development seminar series. I want to say that's in